want you to try. Give this a shot with a hybrid tall plant. Pause me and come back. Okay. At this point in time, you probably noticed that you had 540 tall plants and 460 short plants. Now, a hybrid tall plant crossed with a short plant, that should give us 50-50. Half of the plants should be tall and half of the plants in the offspring should be short. So you write those down as your expected ratio. Now, you total up you have 540 tall and 460 short. Total those up. When you total those up, you get 1,000 plants. Now take those 1,000 plants and multiply them by 1/2. We would expect you would get 500. We would expect to see 500 tall plants. We would do the same thing with 1,000 plants, multiply by 1/2, and we get 500. We would also expect to see 500 short plants, but that's not what we got. We got 540 and 460. So we have to figure out, are these close enough, or is there something else going on here? So we take our observed minus our expected, 540 minus 500, and that gives us 40, and that's our deviation. Observed minus expected here is a -40. That's our deviation there. Then we square these deviations, so +40 times +40 is 1,600, and a -40 times a -40 is also 1,600. We take that deviation squared, we divide it by the expected, so 1,600 divided by 500 gives me 3.2. And here we have 1,600 deviation squared divided by the expected 500, and again it gives me 3.2. Now, to find my chi-square value, I'm going to need to add these two numbers together. So I would say 3.2 plus 3.2 is 6.4. Now again, we still just have two possible phenotypes here. They're going to be tall or short. So that's two categories. 2 minus 1 gives me a degrees of freedom of 1. So I'm going to go over to my table, look right here in this degrees of freedom 1 row. I'm going to look for the number that's closest to 6.4. Well, the closest one we have here is 6.64. That's pretty close. So we look up at our probability and we say our probability is pretty close to 0.01. Now, when I look at this table, remember the light area are things that reject the null hypothesis. We say if you're in this light blue area, this difference is bigger than chance. There's something else going on here. So since this 6.64, which is your closest, this 0.01, is in this light blue area, we're going to say this rejects the null hypothesis. So the observed deviation cannot be explained by chance. Now let's see what happens when we try this with a dihybrid cross. Go ahead and try this problem on your own. Pause me, and then we'll go over it together. So with this dihybrid cross, we are looking at two different traits. We're looking at two plants that are heterozygous for height and seed pod shape. And their offspring should be 1,008 right here. So if you add 587, 197, 168, and 56, you're going to get 1,008 offspring. Now, as we know, dihybrid crosses have a distinct 9:3 to 3:1 ratio. We would expect to see 9/16 would be tall and round, both dominant. We would expect 3/16 to have one dominant and one recessive trait. We would see another 3/16 to have one recessive, the other dominant, and we would expect to see 1/16 both be the recessive traits. And we're going to try to take that into account and we're going to use a table once again. So your expected ratios for this dihybrid cross were 9/16, 3/16, 3/16, and 1/16. We had, if you put in your observed, which again, this is the one with the both dominant traits, one dominant, one recessive, one dominant, and both recessive traits. These are your observed that you were given. We take that total of 1,008 and multiply it by 9/16, and that gets you an expected of 567. We take that total of 3 out of 16, and we take the total of 1,008 plants, multiply it by 3/16, and that gives you 189 for both of these. We take the total of 1,008 and multiply it by 1/16, and that gets you 63. So now we have our expecteds, we have our observed, and we can go through our calculations just like we did before. So we take 587 minus 567, we do observed minus expected, and gives us a deviation of 20. Observed minus expected here gave us 8. Observed minus expected here gave us a negative 21. And observed minus expected here gave us a negative 7. Then we're going to square each of these numbers to get our deviation squared. So 20 times 20 is 400, 8 times 8 is 64, negative 21 times negative 21 is 441, and negative 7 times negative 7 is 49. We then take these deviations and divide them by the expected to get the chi-square value for this category. And you get 0.71, 0.34, 2.33, and 0.78. Again, we just took each of these numbers, the d squared, and divided it by the expected value for that particular phenotype. So this was 49 divided by 63. Now you have to add all of these chi-squared values together. 0.71 plus 0.34 plus 2.33 plus 0.78. That gives us a chi-squared value of 4.16. That was all of these added together. Now, in this example, our degrees of freedom is going to be different because we had 4 possible phenotypes, 4 possible categories. We have these 4 categories, and then our degrees of freedom equation says you take your number of categories and subtract 1. So in this case, it's 4 minus 1 gives you 3 for your degrees of freedom. Now that means I'm going to go over to this row on my chart. If my degrees of freedom is 3, I'm looking for the number that's closest to 4.16. So when I go across, the closest one to 4.16 is this 4.64. So our probability is around 0.2. Now, this is in the dark blue area. So it means everything that falls over here, we're going to say, okay, any difference we have here probably has to do with chance. We're going to say this fails to reject the null hypothesis. And then, so as a result, these observations can be explained by chance.